We've been learning about power sets, and we denoted power sets by this symbol, power set of A, by this P of A symbol. If A were equal to 1, 2 and 3, then the power set of A would be just set of all subsets of A. So I thought it will be a fun exercise today to count the number of elements in PA, in P of A. That is number of elements in power set of A, or equivalently the number of subsets of A, because that will be the exact number of elements in the power set of A. So number of subsets of A, how many are there? This, just some note, I'll take an aside for notation. This is a lot of times denoted by this symbol, n of P of A, and n of A is the notation given for number of elements in A. So n of P of A will be number of elements in the power set of A, and n of A here we know that it is 3. So you just count the number of elements and you use this notation to represent it. It is also called cardinality, but that's just a terminology. You don't need to worry about that, but number of elements are somewhere in a lot of places it's represented by this notation. So now say that I am trying to answer this second question. How many subsets are there possible for my given A, 1, 2 and 3? So I make a little setup for this. I install switches under 1, 2 and 3, simple on and off switches. So this switch can be either on or off, and this is true for all the switches. And I ask you to come up to me, hit all 3 switches in whatever way you like, and whatever position you're comfortable with at the end, you just leave it as such. So maybe you hit the switch this way, maybe you turn this switch on and this one off and this one is off, maybe you left with this. Then I'll say, okay, very good, now you have helped me construct a subset with element 1, and these 2 elements I don't take because they are off, so I don't take 2 and 3. So maybe you left me with this configuration, maybe you left me with this. So on, off and on. That means the subset I'll be collecting will be 1, and 2 I don't collect because it's turned off, and 3 I collect. So this is a subset. So one should convince yourself, convince oneself that all such configurations of those switches of the little game we constructed, all such configurations correspond to a subset of A. What if all the 3 switches are off? You'll get the null set because I don't take any element in my subset. What if all the 3 switches are on? I take 1, 2 and 3, the whole set, which is actually the subset of 1, 2 and 3 itself. We saw this, and null set is also there. So all the configurations, no matter what, will correspond to some subset, and that will be the whole collection we have if we take all of the configurations. So now, do we have an easier problem at hand? Now think about it. We just have 3 switches. Switch 1, switch 2, switch 3, and 3 for each element, right? Now we have translated the problem of 1, 2 and 3 to some random set of 3 elements. You could have A, B and C, alpha, beta and gamma, and in all the cases we'll have 3 switches corresponding to 3 elements. So we're at a good start now. So we just have to figure out how many different possible configurations of these 3 switches are there. So how do we do that? We see that the first switch has 2 possible configurations. So either it can be on or off. So maybe this is on. Or let me just start with a single switch and then we'll come to 3 switches. For one switch, I think I screwed up the spelling of switch. Regardless, so one switch can be either on or it can be off. So I have two different possibilities, two different configurations. Okay, well and good. Now what about two switches? I have two switches. So the first switch could either have been on or off. So say that it was on. Say that I fix this. I say it is on. What about the next switch? How many different possibilities are there? Well, I know there are two, but I calculated it already in my single switch configuration. So this will be for the first switch being on, the second switch will have as many combinations as calculated before. So this is 2, and you turn this switch off and check again for combinations, because this is a new combo we'll be getting. The first switch has been turned off. How many such combinations? Again we'll have all the combinations that we calculated for the single switch. So again we'll have two more combinations. That is, I can write this as, to just see what has happened, I can write this as 2 multiplied by this 2. 2 multiplied by this 2, which is 4. So I'll just write it as 4 for now. So for two switches we'll have 4 combos, and we also know this because it can be either on off, off on, and off off. And for 3 switches, now we are coming to the case that we are interested in, that we asked here. For 3 switches, so the first switch can be on. You fix it, you fix the first switch as in the on position, and then you see how many different combos are there for these 2 remaining switches. Well, lucky for us, we have calculated it here already for 2 switches. So this will be 4 possible combos. 4 possible combos. And for off position, the first switch being off, you'll have as many combos as before, again for 2 switch case, right? So this is plus 4 another possible combos. Hence we'll have 2 times 4 this time. So 2 times 4 from this place exactly, will be 8 different combos. So if I have 3 switches, I'll have 8 possible configurations for switches, and hence for each of the configuration it will correspond to a subset of A, subset of 1, 2 and 3. And hence I can already conclude here that we'll go a step further later, but I can conclude that number of subsets of the power set of this set 1, 2 and 3, or A, is equal to 8, right? We have calculated this just now. And if I just had to give you a general formula for the number of elements in A and the power set of the number of elements in the power set of A, well, you can go a step further if you want. Already here you can see that you are multiplying 2. Here you are taking the power of 2 as there's a single switch, you have 2 to the power 1 here. You are multiplying this 2 again. You are multiplying this 2 again by another 2, and you are getting 2 to the power of 2 actually for 2 switches. For 3 switches you just multiply the case again by 2, so you will get 2 to the power of 3. So for n elements, for n element set, say it is k, see k is my set, n element set, the power set of k, the number of elements in it will be 2 to the power n, because it will be derived from the n minus 1th case. You derived all the switches possibilities and you multiply it by 2, so 2 to the power n minus 1 times 2, you'll get 2 to the power n. If you're not convinced with my argument, you can go a couple of steps further. You can try it for 4 switches. I didn't do it right, so you can try this for 4 switches. I have 4 switches aligned, and the first switch I am just choosing it I am just fixing it in the on position, and I look at all the different combos possible with 3 switches, which we know that it is already 8 from our 3 switch case, and off position will have 8 more combos, which means it is 2 times 8, 2 times the previous 2 to the power 3 thing, which is 2 to the power 4. So for 4 switches I have 2 to the power 4 possibilities. And why am I writing this n element as 2 to the power n is, I think, fairly clear now. And the reason, because I turned this problem into the switch the switch analogy is because this is often used. Even further, you'll have lots of problems in your permutations and combinations chapter, where you'll convert the problem into this basic case problem with switches, and ultimately the number of possible combos will be 2 to the power n for n switches. So I think I have given you the formula that is given in the textbooks, and this was an intuitive explanation without using all the knowledge of combinations and permutations now, but we'll get to those chapters anyway in the future. Thank you for now.